Hello everyone. In the last lectures, we have discussed about measures of central tendency and how to choose the best measure of central tendency. In this lecture, we are going to discuss about skewness. Whenever you run a descriptive statistics function in a software, you will find two values, skewness and kurtosis. These two statistics give you insights into the shape of the distribution. Skewness and kurtosis also very important for data science. Skewness is a measure of the symmetry in a distribution. A symmetrical dataset will have a skewness equal to 0. In statistics, skewness is a degree of asymmetry observed in a probability distribution that deviates from the symmetrical normal distribution in a given dataset. This is Pearson's first coefficient of skewness, mean minus mode divided by standard deviation. We know the relation among mean median mode. Mode equals 3 times median minus 2 times mean. Putting this value of mode in the Pearson's first coefficient of skewness, we will get Pearson's second coefficient of skewness as 3 times mean minus median divided by standard deviation. After calculation the skewness for different problems, if the skewness is between minus 0.5 and 0.5, the data are nearly symmetrical. If the skewness is between minus 1 and minus 0.5, negative skewed, or between 0.5 and 1, positive skewed, the data are slightly skewed. If the skewness is lower than minus 1, negative skewed, or greater than 1, positive skewed, the data are extremely skewed. So here in the number line, we say from minus 0.5 to 0.5, nearly symmetrical, minus 0.5 to minus 1, and 0.5 to 1, slightly skewed. If greater than 1, then highly skewed or extremely skewed, and if less than minus 1, then also highly skewed. In this graph, the orange curve shows skewness as 0, green curve shows negative skewness, blue curve shows positive skewness. The symmetrical distribution has 0 skewness, as all measures of central tendency lies in the middle. So a normal distribution will have a skewness of 0. The similar question what we have discussed in the previous two lectures, we found mean median mode, mean as 226, median as 185, mode as 180. In this question, let us find the skewness. For that, we need to find the standard deviation. For that, we need to find the variance. As we know, the formula is mean minus mode divided by standard deviation. And we know standard deviation is square root of variance. So let us first find the variance. For the given problem, xi's are 160, 150, 170, 190, 180, 200, 180, 220, 210, 600. Let us find xi minus x bar. X bar is mean and mean is 226. So 160 minus 226 is minus 66. And similarly, we will get minus 76, minus 56, minus 36, minus 46, minus 26, minus 46, minus 6, minus 16, 374. Now let us find xi minus x bar whole square. We will have 4, 3, 5, 6, 5, 7, 7, 6, 3, 1, 3, 6, 1, 2, 9, 6, 2, 1, 1, 6, 6, 7, 6, 2, 1, 1, 6, 3, 6, 2, 5, 6, 1, 3, 9, 8, 7, 6. If we add all of them, we will get 1, 5, 9, 6, 4, 0. Now we know the variance formula. Sum xi minus x bar whole square divided by n minus 1. So this is 159,640 divided by 10 minus 1, that is 9. That is 17737.7778. Now the standard deviation sigma is square root of variance. So square root of 17737 is 133.180. So approximately 133 is the standard deviation. Now let us find the Pearson's first coefficient of skewness, that is skewness is mean, that is 226 minus mode, that is 180, and divided by standard deviation, that is 133, which is 0.34586. According to this value, it lies in the number line. You see, from minus 0.5 to 0.5, 0.3 is somewhere here. So it is nearly symmetrical. But if you observe, then obviously it is not symmetrical because there is an outlier which is influencing the curve. So it cannot be 0.34. Then let us find Pearson's second coefficient of skewness. That is skewness equal, we should write here first skewness and second skewness. 3 of mean 226 minus median 185 divided by 133. So this is nearly 0.92. So if it is 0.92, then it is nearer to 1 and it is between 0.5 and 1. So it is slightly skewed. We can transform the skewed distribution to normal distribution by logarithmic transformation. There are some methods to transform the skewed distribution to normal distribution. When data skewed, the tail region may behave as an outlier for the statistical model, and outliers unsympathetically affect the model's performance. The extreme positive skewness is not desirable for distribution, as a high level of skewness can cause misleading results. In positively skewed distribution, the measures are dispersed. The extreme positive skewness is not desirable for distribution, as a high level of skewness can cause misleading results. Another important statistic is kurtosis. Kurtosis is actually the measure of outliers present in the distribution. So in the next lecture, we'll discuss about kurtosis.